And hello, everyone. My presentation is about a novel solar thermal power generation technology using the cascade organic Rankine cycle and the combined sensible and latent heat storage. Thermal power generation is an important utilization of solar energy. The concentrated solar power systems are flexible because they can use relatively cheap material for storage. Their role will be even more important in the future as the renewable electricity in the power grid increase. The red steam generation is one of the CSP technology which can avoid a secondary heat transfer between the solar fluid and the power fluid. In particular, saturated steam generation provides an easy control for the solar field. The DSG technology has reached a high degree of maturity. Some operational DSG plants are listed in this table. Most are located in Europe. The operating temperature and the storage capacity are marked in red. From this table, we can see the DSG system has a lower operating temperature than the indirect solar power generation system using thermal oil and molten salt. So the thermal efficiency is lower. And long-term cost-effective storage is unavailable, thereby restricting the development of the DSG technology. The reason for the low operating temperature is that when the inlet temperature of saturated steam of the turbine increases, the values at the outlets also rise, as shown by the left figure. When the inlet saturated steam temperature increases from 250 centigrade to 311 centigrade, the values goes up from 9% to 18%. A values of 18 is beyond the technical limitation of wet steam turbines. Moreover, sliding pressure control strategy is commonly adopted for the heat discharge of the DSG system. The steam pressure drops almost exponentially with the decrement in water temperature. In order to avoid highly of-design operation and a low thermal efficiency of the power cycle, the temperature drop of water in the high storage tanks is usually less than 50 centigrade. So the storage capacity is limited. To tackle the above challenges, a novel solar thermal power generation technology is proposed. It's the first of its kind. For the solar field, parabolic charge collectors, phase node reflector, and power receiver can be used. For the storage, two-time water storage and phase change material units are adopted. And for the power block, cascade organic Rankine cycle is employed. Steam is generated from the solar field but it's not the fluid of the power cycle. The ORC turbines are in place of the wet steam turbines. Therefore, there will be no jotlet during expansion. Besides, the operating temperature of the storage tank is independent of the steam generation temperature. The hot water tank temperature in the high temperature tank can be 100 centigrade lower than the steam generation temperature. So the storage cost is reduced. The proposed system has 4 main operating modes. In the normal operation, water in the low temperature tank is pumped into the high temperature one through the solar field. The mass flow rate through pump 4 can be adjusted depending on solar radiation. The solar heat is stored in the high temperature tank and PCM's unit. The steam generated in the solar field is used to dry the cascades ORC, and the cascades ORC operates at a rated power capacity. Stable power conversion can be guaranteed over a wide range of solar radiation. There are 3 steps for the discharge process. In the first step, the latent heat from the PCM is released to dry the cascades ORC. As more and more PCMs accumulate on the heat exchanger, the thermal resistance increases, leading to a decreasing power output. When the power output drops to a certain level, for example, 60% of the normal output, then the second step, heat discharge, begins. Both the latent heat from the PCM and the sensible heat from the hot water tank are used to dry the cascades ORC. Hot water in the high temperature storage tank flows into the low temperature one, and the heat is used to dry the bottoms ORC. In this step, the power output of the PCMs is still decreasing due to an increasing thermal resistance of the PCM. The bottoms ORC, on the other hand, can operate under normal conditions. So although the top ORC power output decreases, the total power output of the system is still high. When the heat discharge from the PCMs is completed, the third step, heat discharge, begins. Hot water in the high temperature storage tank flows into the low temperature one, and the heat is used to dry the bottoms ORC. The discharge process indicates the proposed technology can overcome the challenges of the PCM in the CSP's application. The power output of the proposed system on a typical day is illustrated here. In the morning, when solar radiation is weak, the solar heat is collected and stored either in the hot water tank or the PCM's unit. Hot water in the high temperature tank is used to dry the bottom ORC with a power output of 6 microwatt. When the solar radiation becomes stronger, for example, higher than 400 watt per square meter, the solar heat will be sufficient to dry the cascades ORC, and the power output reach 10 megawatt. The residual solar heat is stored either in the PCM's unit or the hot water tank. In the evening, when the solar radiation gets weaker, the first step, heat discharge, begins, and the power output drops from 10 megawatt to 6 megawatt. And then the second step, heat discharge, starts. There is a sudden increase in the power output at the beginnings of the second step, heat discharge, because the bottom's ORC shifts from an off-design operation to the normal operation. When the heat discharge from the PCM comes to an end, the third step, heat discharge, begins, and the power output remains at 6 megawatt. The advantages of the proposed technology includes a significantly increased steam generation temperature and storage capacity. The steam generation temperature can be elevated from a conventional value of 270 centigrade to 370 centigrade with a higher efficiency. The storage capacity can be increased by 400%. A case study is presented here. Toluene is used as the fluid for the bottom and the top ORC. The steam generation temperature is 311 centigrade, while the hot water tank temperature is 270 centigrade. The evaporation temperature of the top and the bottom's ORC are 301 centigrade and 180 centigrade, respectively. The efficiencies of the turbines, pumps, and generator are 85%, 75%, and 95%. Based on these conditions, the thermal efficiency of the cascade ORC is more than 33%, which is comparable to the efficiency of an indirect solar thermal power generation system using thermal ore. And the bottom's ORC efficiency is more than 23%. Another case study is presented here. Toluene is still used as the fluid of the bottom's ORC. Thermal ore, on the other hand, is used as the fluid of the top ORC. The operating conditions of the bottom ORC are the same as those in the first case. For example, the evaporation temperature is 180 centigrade. The evaporation temperature of the top ORC is 360 centigrade using thermal ore. Thermal ore is a widely used solar fluid in CXP application. It's a mixture of biphenyl and diphenyl oxide. It can be used as both the liquid and the vapor phase heat transfer. It has excellent thermal stability at temperatures up to 400 centigrade. So the steam generation temperature is 370 centigrade, while the hot water tank temperature is still 270 centigrade. The thermal efficiency of the cascade ORC is more than 37%, which is quite high. Notably, the proposed technology has the potential to tackle the challenges of a conventional system and also the PCM in the solar power application. Even without the PCM, the proposed technology is still more advantageous than a conventional VSG technology because it has a unique heat discharge process. Hot water in the high temperature tank is used to dry the bottoms ORC. So the storage capacity can be significantly increased. The temperature heat transfer diagrams in the unique discharge process are displayed here using different ORC fluid. Waters leave the high temperature tanks at a temperature of 270 centigrade. Water temperature at the inlet of the low temperature accumulators varies with the ORC fluids. The temperature drop from the high to the low temperature tanks can be more than 200 centigrade, which is obviously much higher than the temperature drop of water in a conventional VSG discharge process. The storage capacity is therefore increased with stable power output. We have also calculated the equivalent payback periods in regard to the use of the unique discharge process. More solar collectors are required to harness solar energy for the unique discharge process. The equivalent payback period is defined as the ratio of the additional investment to the annual revenue. In the simulated areas, the equivalent payback period is usually less than 5 years. A comparison between the proposed technology and an operational VSG plant, PS20, which is located in Spain, is made here under some given conditions. Both systems use tower receivers to harness solar heat and water steam as the solar fuel fluid and has the same size of the high temperature tank and the rated power output. For the proposed system, the steam generation temperature is 370 centigrade, while it's 270 centigrade for PS20. The thermal efficiency in the normal operation is more than 37%, while it's probably less than 30% for PS20. The storage capacity is more than 5 hours, while it's 1 hour for PS20. Based on the comparison, the proposed system is expected to have a shorter payback period than PS20. In summary, the proposed solar thermal and power generation system tackles the challenges of conventional DSG technology. It eliminates wet steam turbines, so there will be no jobless during expansion. And also, the ORC turbines can be more cheaper than the wet steam turbines. And the wet steam turbines are very challenging. And the proposed system has a higher thermal efficiency and storage capacity. Its efficiency will be even higher in the future via optimization. So I think it's quite promising. The above are all my presentation. Thank you. You are welcome to ask questions.